Hello, welcome to this video. So this is a follow-up video to the video on Maxwell's equations, in which we showed that the speed of light is a speed which all observers, at least who are not accelerating, would agree on the value of. And this is a follow-up video to that where we try to build from the universality of light, or the speed of light, other constants which all observers would agree upon, which is very important in special relativity when we try and describe the universe in terms of equations that do not depend upon the observer's velocity, which is very important because we want to have a description of a universe which will not depend on how quickly you're moving through the universe. Otherwise, we would need to have, a whole, set of equations for each distinct kind of velocity, which would be incredibly time-consuming. So, it's very important to look at invariant quantities and special relativity, and that's the main purpose of this video. But to get there, we have to start with the speed of light being a universal constant, our kind of principle of relativity, special relativity anyway. And then from that, we'll be building up kind of a notion of space-time and describing distances between events in space-time to accommodate for this kind of constant speed of light. And in this process, we'll be talking about finding the length of vectors, which will introduce us to the strange world of hyperbolic geometry, in which, as you can see in the figure here, triangles have internal angles which won't add up to 180 degrees, and there is many strange effects of hyperbolic geometry, including some very bizarre aspects of rotation in a hyperbolic space, which we'll kind of mention in this video but explore properly in the next one. So don't worry if you don't know what a vector is, what spacetime is, or hyperbolic geometry. We'll cover all of that in this video. So this video will be about things which are invariant in kind of like space-time, or at least things that all observers who are not accelerating will agree on the value of. And this will lead us to a discussion also of why we can't trust things like time intervals and space intervals, and so we'll mention time dilation, length contraction, and all that cool stuff along the way, and also talk a little bit about a thought experiment involving kind of humans running away from laser beams. Slightly dark, possibly, but then physicists do love generally science fiction, and also have a kind of fondness for life or death scenarios because it makes physics very exciting. It definitely gets the imagination fired up. I mean, my videos are not nearly as dark as some of the scenarios you might be asked to explore in a physics degree. But hopefully, this video will be fun, fairly light-hearted, but quite informative too. And it's probably going to be a bit longer. We have a lot to cover, but well, it will hopefully be fruitful. So, as we said at the start of the introduction, the cornerstone of special relativity is that all non-accelerating observers agree on the speed of light. So it doesn't matter how fast you try to run away from a light beam which is moving towards you, it will reach you in the, it will reach you with the exact same speed as if you were, completely stationary. And that introduces some really bizarre kind of consequences, as we will see during this video. And we will see more of kind of the experimental context, of these ideas once we have gone through the theory in the next few videos. So let's kind of take the cornerstone of special relativity, the universality of the speed of light, which, if you would like some convincing of, the previous video and the playlist derives this from Maxwell's equations. But let's kind of take it as true that the speed of light is a speed which all observers will agree on, no matter their velocity, providing at least they are not accelerating. Well, we can then kind of picture a particular scenario. So, in this scenario, there is an alien, and the alien is firing a laser beam towards a fleeing human who is trying unsuccessfully to run away from the light beam. The human can't run away from the light beam because he can't move faster than the speed of light, a consequence we will develop during this playlist. But anyway, the human is attempting to run away from the light beam because this light beam is made of, say, very high frequency dangerous light. And we can consider the speed of light from the person's perspective, the human's perspective, and also from the alien's perspective, who is kind of the one holding the laser gun. Well, our intuition, which is wrong, turns out, would say that whilst, even if it may not be possible for the human to outrun the light beam, if they are running away from the light beam, then the light beam should seem to approach them, at a speed that is slower than the light beam is moving relative to the alien, because the human's trying to run away from the light beams, and so you would think that the speed the human would see the light beam coming towards him should kind of diminish as the human speed increases. But the principle of relativity says no, this can't happen. All observers have to agree on the speed of light, and this will lead to some very strange consequences we will explore in this playlist. So, that's rather bad news, I suppose, for the human anyway. But now if we want to turn this idea into an equation, the universality of light into the speed of light into an equation, then we have to kind of define speed, because this principle is all about the speed of light. Well, speed by definition is just distance over time. So, using our analogy of the human running away from the laser beam and the alien being the one that kind of fired the laser beam, we can consider the human as kind of moving, if you like, and the alien holding the laser gun as stationary. Now, you could argue it in the reverse. You could go, well, if we could set up some coordinate system that follows the moving observer. So in other words, if you like, in the moving observer's reference frame, the moving observer might be stationary, because we define this coordinate system to move along with the moving observer. So in this coordinate system, the moving observer isn't changing his position, so the moving observer would be stationary, and in this coordinate system it would be the ground as well as the alien, which is the thing moving away from the human. However, in truth, it doesn't really matter which way round you do it, The important thing is that if we treat, say, the human's coordinate system, in other words, its reference frame as being the prime reference frame, and the alien's reference frame as being the non-prime reference frame, so, has coordinates without dashes above it, then we can always write this equation where dx, or dx prime, measures the distance the light beam has moved, and dt, or dt prime, measures how long it has taken for the light beam to move that distance. So what this equation says is that the speed of light is the same for both the alien and the human, where for the human, the speed of light is the distance the light travels according to him, divided by the time it would take divided by the time it would take for the light to travel that distance. And for the alien, the speed of light is the distance the light travels according to the alien, divided by the time it takes the light to travel that distance according to the alien. And both these speeds are kind of agreed upon by the alien and human, so they're the same. And it's this kind of equality which will actually allow us to develop the idea of distances between events in space-time, so kind of like how much in space-time the event of the laser beam being fired from the gun is separated from the laser beam inevitably hitting the human. So this is kind of like the core equation which will allow us to kind of talk about space-time and space-time intervals. And we'll be developing this equation on the next slide and seeing why, if this equation is true, we can no longer consider really space and time, or in other words, distances the laser travels and the time it takes for the laser to travel that distance to be values the human and the alien would agree on, even though the speed of light is something that they both rather bizarrely do agree on. So we mentioned before the idea that we could write this equation for light. Now it's worth saying when we're doing this, when we say x, we are not talking about the distances either observers, so our human or alien move, we are talking about the distance the light beam moves. So that's important because we're going to now define something called the space-time interval, but it'd be particularly for light because it's to do with the motion of the light beam or the laser beam in our context itself. So if this equation is true, then evidently this following equation, just by rearranging the top equation, would also be true. And what this gives us the space-time interval for, well, between events according to light. So, this could be between any two events because this will be true, no matter what distances dx or times dt we're talking about. So for example, the space-time interval between the alien firing the laser beam and the laser beam tragically hitting the human would be zero, but you have to define those two events, any events in space-time. And when I say an event in space-time, I mean something that happens at a particular location and at a particular time. So this is that if we could define the space-time interval in something like an expression of a time-like component minus a space-like component, or I should say a time-like component squared minus a space-like component squared, then for light, at least when we're defining the space-time interval in terms of light's motion, we're always going to get zero. So what that means bizarrely for light is all events in space-time occur at no distance apart, which is rather bizarre. But for our purposes, because we are not light beams, indeed this is really a hypothetical extension of relativity because we can't really directly test this because we can't have any measuring instruments that move at the speed of light because we don't know how to make measuring instruments that are massless at the moment at least. We're really interested in a space-time interval where dx won't refer to how far a light beam travels, but would refer to how far a moving observer would travel, for instance. Now, because in our previous example, when I was kind of imagining an alien firing a laser beam at a human, it made kind of intuitive sense so that the human would just run away, but along the same axis the laser beam was moving at. We had the human moving in an axis that was kind of parallel to the direction and motion of the light beam, and that introduces a lot of complexity if we actually want to get to a space-time interval for a moving observer, thanks to effects of length contraction, which I'll talk about a bit in the next slide. or at least mention. So if we could talk about the space-time tour for kind of observers, then really we want the motion of the moving observer, if you like, to be perpendicular to the direction and motion of our light beam. That way we don't have to worry about length contraction effects. So I thought, how would I extend my story to accommodate for this? So this is what I came up with. In this kind of next chapter of our kind of heroic adventure, with our human running away from the alien, which I suppose might not be very heroic, but at least a very wise human. You know, if you ever face an alien with a laser gun, run away. Maybe not in the same direction as the light beam, because if you know special relativity, you'll know you can't outrun light. But do run away. But let's suppose that the human has kind of ran onto a train, and the alien has kind of like caught up with him, entered the same carriage on the train. But then the human escapes through a shaft on the kind of like roof, if you like. I should say like I don't know, ceiling. I don't know what you would call it, but the upper bit of the train, and has escaped through it, and then shuts the kind of like the bit of the upper train, the flap he had to open to get out of the train, and he closes it, and then he safely jumps off of this fast-moving train and runs to a platform, and he happily watches the alien go by on this kind of moving train. Now the alien doesn't know that the human has successfully jumped off the train, because the train was moving quite fast, so the alien presumes the human wouldn't have done this, and it's just standing on top of the train above the alien. So the alien keeps firing a laser beam at the ceiling of the train vertically upwards, not knowing that the human is safely on a platform watching the train with the alien inside it moving by. So this is our setup. So now in this setup, the alien is the moving observer, if you like. So we have prime coordinates for the alien's measurements of events, and the human is the stationary observer. He's watching the train go by, so his coordinates are not primed. So important distinction from before. Well, we can now consider what would the space-time interval between events be for the alien and the human, where the kind of events we're considering is kind of like, well, our first event is the alien firing the laser beam from the ground. Say it's a very small alien, so near ground level, and then the final event is the laser beam hitting the ceiling of the train. And so we're trying to find an expression for the space-time interval between those two events. Now, from the alien's perspective, the alien considers himself relative to at least the carriage he's on and the light beam to be stationary. So he just thinks he's sending the light beam just vertically upwards. The motion of the train can be completely ignored, because from the alien's perspective, the train and the carriage he's in is stationary. Because the train and the carriage are not moving away from the alien, because the alien is in the carriage. There's something be going terribly wrong if the carriage was moving away from the alien. So the alien is in a secure train, so the carriage is stationary relative to the alien, and therefore the light beam, when it sends it vertically upwards, is just kind of hitting the ceiling and then possibly bouncing vertically down. And again, using prime coordinates for the alien, because now he's the one, well, I say he, I mean, now the alien is the one moving, we can say that the time interval between the laser beam being emitted and the laser beam hitting the ceiling from the alien's perspective is dt prime, and because the light is moving at a speed c, the distance, the vertical distance of the carriage is going to be c times dt prime. It's just distance equals speed times time. From the human's perspective, however, the light beam is not moving vertically up and down, because the human, being stationary, sees the train along with the alien and the light beam moving with some horizontal velocity. This is a horizontal component to velocity. Because the train is moving kind of horizontally along, The train isn't climbing into the clouds, so it hasn't got vertical velocity, it's moving horizontally. And so the human is going to see the light beam having both a horizontal component due to the motion of the train, but also a vertical component due to the fact that the alien was trying to fire the light beam vertically upwards. So the light beam is going to seem to move diagonally. And the distance the light beam has moved vertically, the distance the light beam has moved horizontally between the light beam being fired and hitting the ceiling, according to the human's perspective, I'm going to call dx. Now, the distance the light travels is kind of a diagonal distance, which is going to be c dt, where dt is the time interval from the human's perspective. But c dt is kind of the length of this kind of diagonal kind of line. Now, if we put c dt prime dx and c dt together, we see we form a right-angled triangle. That is assuming the height of the carriage is the same from both the human's and alien's perspective, but because the carriage is not moving vertically, this can be taken as true. There is no length contraction or strange effects in the vertical direction anyway. That's why I picked the train moving horizontally whilst the alien fires the laser beam vertically upwards to avoid complexities of length contraction. So, putting all these sides of our right-angled triangle together, we can see that CDT would be the hypotenuse of our triangle, dx would be the horizontal base of our right-angled triangle, and CDT prime would be our kind of vertical line of our right-angled triangle. And then using Pythagoras' theorem, we can relate all these sides together, and we can do that because these are length in three-dimensional space, and we calculate length in three-dimensional space using Pythagoras' theorem. And when you do that and rearrange a bit, you end up with this expression. Now, this expression is a general expression for the space-time interval for observers in different reference frames, and we see that kind of, because of this equality, the space-time intervals are the same. Now, they're not going to be necessarily zero. In fact, because the train is moving at a speed less than the speed of light, dx is always going to be less than cdt. Light is always going to move a greater distance than the amount the train moves, so the space-time interval is always going to be positive. Now, it's also worth saying that you might think that there's a bit of anti-symmetry here, because you might think we should have c squared dt prime squared minus dx prime squared is equal to c squared dt squared minus dx squared. You might wonder, where is the dx prime gone? Well, the dx prime is kind of secretly here, but the dx prime would refer to the horizontal distance the alien thinks he has been moving, or equally because he's co-moving with the light beam, the light had been moving, at least co-moving horizontally. But because the alien considers himself as stationary, and also the light beam as being, having no horizontal velocity anyway, dx prime, that is the horizontal distance the alien thinks he has travelled, is 0. And therefore there is actually a dx prime here. It's just dx prime is 0, so I haven't included it. It is worth saying generally the space-time interval, when we're saying it's the same between the primed and non-primed reference frames, when you're making that statement, you would use a prime. Well, you would include a dx prime. But because we're considering the alien as, thinking that he is stationary, dx prime would be 0 in this case. However, it's worth saying, if we consider that, say, a rival alien on a third train, and this train was moving relative to the alien's train, and we ask about space-time intervals between events that happened on that third train from the human and the alien's perspective, then the space-time interval for both the human's perspective and the alien's perspective would have to include, spatial distance terms. So for the alien, we would have a dx prime, because this third train would be moving relative to the alien. So events on this train, there would be a horizontal, displacement between, one event and another that occur on the third train according to the alien's perspective. So if you've got 3 observers, which is rare, but you could have it, and you're comparing events in 3 observers, or you've got 2 observers which are moving relative to some event in a third reference frame, then you would include a dx prime. However, because often in relativity we're only concerned with 2 observers, one of which we can consider as stationary, often when we write the space-time interval being the same for both observers, we write it in this form, where dx prime isn't included because dx prime is kind of taken to be 0. And this equation is very, very special because it tells us, since we're, by relativity, we have to take C to be the same for the human and the alien. Because of that, it means that dt prime and dt have to be different if dx isn't 0. So in other words, providing the alien has some non-zero horizontal velocity relative to the human, then the time it takes for the light to travel to the ceiling from the alien's perspective will be different to the time it takes for the light to travel from the human's perspective. And this brings into the equation the idea of time dilation. So whilst both the alien and human agree on the space-time interval between events, they do not agree on the time interval between events, something we find really bizarre because we're kind of used to thinking that time moves at the same rate for all observers, but it doesn't. We see this, for example, in muons taking much longer to decay than we think they should, and that's related to the fact that muons are moving at a speed, a very, very fast speed relative to us, and the effect really kicks in as the velocity of the moving observer approaches the speed of light. And we should see that time dilation should depend on not just dx, which relates to the velocity of the moving observer, but also to the value of the speed of light, thanks to our equality of the space-time interval here, because this equality explicitly involves the speed of light. So it's not too much of a surprise that it's how big something's velocity compared to the speed of light is that will indicate whether effects of time dilation are important or not. And it's a fact that when we move, even on the London Underground or something, or even on a plane, we're moving at a speed which is far, far below the speed of light, that we don't really notice these time dilation effects much in daily life. Right, so we've talked a little bit about the space-time interval. Let's now talk about it more explicitly. So before we considered you know, the alien in this train, where this train was moving along, you know, the x-axis. But say we have some much more complicated motion and the train is moving along the x, y, and z axes, then we have to, our distance no longer be dx. So our distance squared is no longer be dx squared. Our distance squared is going to be the sum over all axes of the distance in that axis moved squared. So in other words, the spatial distance moved by the moving observer is going to be the sum over all possible spatial axes. So the sum over I of dxi squared, where dxi is, you know, the motion in the ith spatial axis. So for our universe, since we have 3 dimensions of space, I can be 1, 2, or 3. You know, there's only 3 independent axes of motion allowed. However, it's useful kind of grouping the space terms together and considering, well, this quantity, which is preserved in both the primed and non-primed reference frames, is just a measure of kind of like interval in time minus a measure of a kind of distance in space. Although those distances should be squared. So both sides of this equation we have a space-time interval. On the left-hand side, where we don't have any primes, we have the space-time interval according to a stationary observer, so like the man, and on our left-hand side we have the space-time interval according to a moving observer. It's worth saying, if we're talking about events which happen in the moving observer's own reference frame and not a third moving observer, then as we did with the alien, we would set dx prime to be 0, in which case dt prime would be the proper time. But as I say, that's not a given, because, you know, we could be talking about motion that occurs, you know, in a third, you know, moving reference frame, meaning that this kind of motion would move at a non-zero distance in space according to both the stationary and at least one of our moving observers, in which case we couldn't set either dx or dx prime to 0. So it's worth saying, when you're doing special relativity, you do really have to think carefully what reference frame you're dealing with, and note that, you know, if you're dealing with a moving reference frame, often because we're just interested in comparing a stationary observer to a moving observer, you can then just set dx prime to 0. But you have to be careful, because, you know, it's not a given. And, you know, a moving observer can still see something else moving relative to them, you know. You know, for example, if I'm on a train moving at 20 kilometers per second, yes, kind of like my laptop might be stationary in my reference frame, so I might say dx prime is 0 if I'm talking about the motion in my laptop. But if both somebody on the platform and me are talking about, say, a balloon in a second train, and that second train is moving at 40 kilometers per second relative to the stationary observer, then I would see this train moving. This train would have some relative motion to me. And so if we were talking about, you know, the space-time interval between kind of events concerning the balloon, then, you know, both the stationary observer and me would say that the spatial distance between the events would be non-zero, so neither of us would be able to set our, our distances in space to zero between those events. So that's an important thing to note. I say that and go through that in detail because it's something I won't often go into, because that's only if you've got 3 reference frames where you need to worry about that, and very rarely will we worry about 3 reference frames. Usually 2 will be good enough. Now, as I say, we call this quantity where we're doing c squared multiplied by some time interval squared minus the kind of spatial distance that something has travelled between that time interval squared. We call that collection of terms the space-time interval, which has the symbol ds squared. Now, it's worth saying there are a few subtleties here with this notation. So firstly, the idea that we're doing kind of, if you like, a time-like separation minus a space-like separation. Now I'm doing that because since nothing can travel faster than the speed, well, at least since nothing we know about yet, at least, can travel faster than the speed of light, doing the subtraction in this order will ensure that ds squared is positive. Because if we take dx to be how far something has moved, since the amount it has moved will always be less than the amount light would have moved in that time, because the object can't move, it can't even get to the speed of light, and it's always going to be moving slower than the speed of light. Then when we do c squared dt squared minus the sum of dxi squared, we're always going to have a positive number. So this ensures that ds squared is positive, so our space-time interval is positive, and it's nice to talk about positive space-time intervals. The other reason for defining the order of subtraction this way and not doing, the space-like separation squared minus the time-like separation squared, is that whilst it's standard to call ds squared the space-time interval, you might be thinking, well, ds squared has units of meters squared. Really, a interval should have units of length and units of meters, and you can do that. Sometimes, although it's not standard, you could see, written that ds is the space-time interval. As I say, that's not standard procedure, but it sometimes is used. And if you're defining ds to be the space-time interval, you definitely want ds squared to be positive. Because whilst if you're just sticking with the space-time interval to be ds squared and ds squared is negative, that's not too bad, although it's slightly inconvenient. If you're defining the space-time interval to be ds and ds squared is negative, then you're going to have to conclude that your space-time interval is imaginary. That is, it's the square root of a negative number. So to ensure that ds squared is positive, to make it, straightforward to talk about the space-time interval, and particularly to allow for the fact that if somebody wants to talk about ds as the space-time interval, that ds is guaranteed to at least be a real number. When we're talking about ds squared, we usually do the time-like separation minus the space-like separation. Now, if you're interested in looking at, hypothetical particles called tachyons, which would travel faster than the speed of light, you may well want to reverse the order of subtraction. But as we're not worried about tachyons, at least for this video, we're going to stick with this kind of convention. Now, as we said before, particularly if we're considering events in the moving person reference frame and considering the space-time interval between those events, then we're going to be able to set usually dx prime to 0, leading to an equation which clearly goes, well, dt prime is going to have to be different from dt, and what that means is that time from the perspective of the moving observer is going to have to be different in terms of the rate of time relative to the, well, rate of time compared to the stationary observer. So time can move at different rates. And this really means that time can no longer be treated as an invariant quantity. In that, yeah, we all know, for example, if you're talking to a friend who's in another country, the literal time isn't going to be the same across all places in the globe, but a surprise of special relativity is that also the rate of time can be different, and clearly the rate of time is going to become more and more severely different the bigger dx grows, assuming we're setting dx prime to 0. And dx refers to the velocity of the moving observer, and as dx will grow when the velocity of the moving observer increases. So in other words, we would expect time dilation to become more extreme the quicker the moving observer goes. And it's not too much of a surprise, although we will see more explicitly later on, but it's not too much of a surprise that it's really the fraction of the moving observer's velocity relative to the speed of light, so relative to c, that actually counts. And we could kind of infer that because we have c already in our expression, so the speed of light should have something to say on how significant this time dilation effect should be. And it's because objects tend to move much slower than the speed of light, we don't really observe this effect usually, but we'll be going into more detail of that later. This is more just about the space-time interval, but it's worth saying we can already see indications by looking at the space-time interval that time is, well, the rate of flow of time is not an invariant quantity. Now you can also come up with a different thought experiment to the one we've done, and conclude that you can make a similar statement about space, or I should say distances between events in space. So, in other words, the distance between events, distance in space is, just like the rate of flow of time, not something all observers will agree upon. It depends upon your velocity. And this leads to the idea of a length contraction. But since time intervals are not invariant, nor are space intervals, but the space-time interval is invariant and is agreed by observers of differing velocity, what that tells us is if we're going to write equations of motion in physics, they should really relate to either the space-time interval or some other similar kind of constants constructed in space-time. It tells you that the space-time interval is actually the physically meaningful quantity, because unless you want to have a different set of laws of physics for every single possible velocity, you're going to want equations that make reference to things that all observers will agree upon, which turns out we're going to have to use quantities like the space-time interval or other things like that. And, we can no longer write equations that are going to be valid in terms of special relativity, which will make independent reference to time and space, because we can see both time and space are relative, whereas the space-time interval is not. And so that's kind of the take home of this kind of bit of the video. And now we're going to talk more about kind of like what the space-time interval says about the geometry of space-time, and that will lead us directly into 4 vectors. So now we're going to talk about how what we have said indicates that if we're going to describe distances between events in space-time using a space-time interval, then space-time is not going to be a Euclidean space. It's not going to have a Euclidean geometry, or in other words, it will not obey Pythagoras' theorem. So, as we've said before, all observers agree on the space-time interval. The space-time interval clearly is some measure of distance, and it's to do with measuring kind of distances between events, so things that happen at a particular point in time and a particular location in space. And since the space-time interval, unlike the time interval or the distance, is something all observers will agree on, it makes sense to define the space-time interval as the meaningfully significant measure of distance in space-time. So if you want to know how far apart events are, you would want to use the space-time interval to at least talk about something that all observers are going to agree upon. Now, the kind of distance from one event to another is kind of like the length of a vector, where this vector is an arrow that links one event to the other event. Like this vector starts at one event and ends at this other event. So we can rethink of the space-time interval as really the distance of a vector in space-time. Now, because this vector links events with 4 components, 3 components of space saying where the event happens, and 1 component of time saying when the event happens, because it's linking 2 events, each of which have 4 coordinates, this vector is moving through space with 4 dimensions. So we would say that this is a vector living on a space, although now when I say space I don't mean physical space, I mean mathematical space, a mathematical 4-dimensional space. So we would call this a vector which lives in 4 dimensions. And the size of this vector is the space-time interval, which, as we've said, is a size which all observers agree upon. Now, if we're talking about something that all observers will agree upon, no matter their reference frames, so no matter what coordinate systems of space or time they're using, providing they're not accelerating, then clearly this kind of length of this vector is something that all observers agree on, no matter their own reference frames. And so the length of this vector is acting like a scalar quantity. It's not changing when we change our reference frames, or in other words, our coordinate system. Much like we would expect with an ordinary vector. If we had, a vector that you plotted on paper, and then, you rotated the paper, so you've kind of rotated your coordinate system, the vector might appear to point along different directions. So for our context, its time and space components might change, as we have seen would happen if you alter your velocity. However, the length of the vector, so the space-time interval between the events, remains, preserved. So the space-time interval is acting like a scalar, which is about the length of a vector living in 4-dimensional space connecting one event to another event. Also a clue is that we're talking about kind of a scalar value of length, is to get the length of a vector in 3-dimensional space. You do something like the length squared is equal to some combinations of the components of the vector squared. and we've got the components of our vector in four-dimensional space that we've had to square and combine together to get this space-time interval. So this space-time interval is acting like a scalar value associated with the length of a vector. And so our equation for the space-time interval does kind of look like a scalar product, which is an operation you can use to find the length of a vector, when you take the scalar product of a vector with itself. However, there is a slight subtlety from how we would usually calculate the scalar product, I mean, at least in terms of, three-dimensional space or, Euclidean geometry. Because if we're finding the length of the space component to our vector, we do as we usually would. We consider space to be Euclidean, and therefore the total distance squared is equal to the sum of all the individual component distances squared. This is just Pythagoras' theorem, but I put I because I don't want to assume we have three dimensions of space, even though I think for all of this playlist we will assume we do. But for those of you who are interested in string theory or something, it's worth putting I, because we can't be sure we live in three dimensions of space. It's just there definitely are at least three noticeable macroscopic dimensions of space. So we have a kind of interval in space which is defined according to Pythagoras' theorem. However, when we found the space-time interval, so the length in four-dimensional space-time, we didn't add the time-like component to our, vector in four dimensions to the space components, as we would if space-time had some kind of Euclidean geometry and therefore was obeying some kind of Pythagoras' theorem. No, instead we had to take this time-like term, square it, and then take away the square of the space-like terms, and it's this minus sign which is jarringly different from how you would collect components of a vector together to get the length of a vector in Euclidean geometry, and it's this minus sign that makes all the difference. It means that space-time, the geometry of space-time, which is based upon a rule for calculating distances between points or events in space-time, does not obey Pythagoras' theorem. There is no consistent way to make it obey Pythagoras' theorem because this minus sign is crucial. Therefore, space-time does not have a Euclidean geometry. It does not obey Pythagoras' theorem because of the natural way we have defined kind of distance in space-time. Instead, this space-time is something called hyperbolic, has a space which goes by many names, but one name is a hyperbolic space. And we're now going to look at more details of exactly what this hyperbolic space is. And it's actually the fact that we're dealing with a hyperbolic space that means that our scalar product telling us the length of a vector, so, at least for a vector linking events in space-time, it would be, the space-time interval looks kind of peculiar with the minus sign. It's because we're not working with a space with Euclidean geometry. We're working with a hyperbolic space. So we talked about the space-time interval. We talked about the fact that space-time is not Euclidean. Now we're going to see an example of quite how non-Euclidean it is fairly visually, because I know this has been fairly abstract and very wordy before. So that's bringing a bit of visualization to see how different hyperbolic space is. So for this, we're going to recall our notion of distance in space-time. So we say that the distance squared, although sometimes people are rather, lax and just say the distance. In space-time, between events in space-time, is given by this equation where dt refers to the time intervals between those two events in a particular reference frame, and dx refers to the spatial distance between those two events in a particular reference frame. Now, to see how strange this rule for calculating distance is, we can look at, well, if we define this to be a measure of distance, what does a circle look like in this kind of space? Well, if you think we consider a circle, or at least, a circle with equivalently a circumference. So, I should say, we define the circumference to be a set of points which are all equidistant from some central point in our circle. And we often, for convenience, place the central point at the origin of a coordinate system. So for any space, if we have a notion for how we calculate distance in that space, we can say, well, a circle, well, the circumference of a circle at least, is the set of points for which that distance from the origin of our coordinate system is equal to some constant. You don't care what that constant is, although, at least in Euclidean space, the bigger the constant, the larger the circle. But the important thing is, to get a circle, we just set the distance from the origin of our coordinate system, so our interval in that space, if you like, to equal a constant. And we can do this with our hyperbolic space-time, and we'll see very quickly why we called it hyperbolic. Because it turns out that all of these lines or curves here are examples of circles. As strange as that might sound. So let's get rolling with this. So our straight lines are circles. Or really I should say they form a single circle in hyperbolic space, because both these lines have the same value for ds, and that value is 0. And remember that this is kind of the space-time interval between events according to light. So, according to light, the space-time interval between any two events will lie somewhere along these two lines, these two diagonal lines. And the interesting thing is, if we're going to use Euclidean terms, where the radius of the circle would be the same thing as your interval in that space, then these hyperbolic circles, if you like, which are straight lines, have a radius of 0. So they're at 0 distance from the origin of our coordinate system. Now in Euclidean space, there is no extended object which is at 0 distance from the origin of the coordinate system, because the only way you can get 0 distance using the Pythagoras' theorem is to set all the components of your vector with that distance as its length equal to 0, meaning that your entire vector will lie at the origin of the coordinate system. The only point which has 0 distance from the origin of the coordinate system in Euclidean space is the origin of the coordinate system itself. All other points are at a non-zero distance from the origin of the coordinate system. However, that's clearly not the case with hyperbolic space, as we can see. So, one bizarre thing is that one circle, for example, the circle of 0 radius, when transferred into hyperbolic notion of distance, is actually given by what to us look like, and at least in Euclidean sense, are straight lines. It's worth saying when I say straight, I mean what they look like to us using our notion of distance. So they're straight in Euclidean space. However, they're not straight in hyperbolic space, because as I say, these two lines together form a circle. So that's the other thing to bear in mind as well. Curvature is again dependent upon the space you're talking about. Now, if we look at another circle, let's say, for example, a circle, if you like, which again, using Euclidean language, has a radius of 10 units, then the hyperbolic version of that circle is these kind of curved lines, which are hyperbola. Now, it's worth saying straight lines are also an example of hyperbola, just very specific ones. A more general hyperbola will have these kind of curves, these kind of curvature. The equation of a hyperbola in at least Euclidean space is just it's just your x coordinate squared minus y coordinate squared is some constant squared. So we can immediately tell from that, well, if we draw a hyperbola, then that hyperbola is going to refer to a constant spacetime interval. If we're saying our coordinate system is given by, axes in spacetime. And an interesting thing about these kind of hyperbola is if we carry on this to infinity. So if we had, say, a hyperbolic version of a infinite circle, then all these hyperbola would indeed meet. So in the case where you have a space-time which is infinite, and you're concerned with kind of like events in space-time which are infinite intervals apart, then the circle, if you like, of all those points does form, even when we look at it in a Euclidean way, a closed curve. Because these hyperbola will meet if we allow them to stretch to infinity. However, for any finite, circle, if you like, in hyperbolic space, it's constructed from these individual hyperbola which will never actually meet. So another strange thing is the version of a circle in hyperbolic space, unless we're worrying about a circle with infinite radius, is actually a disconnected shape. It has gaps in it. Now, all of this has been to try to emphasize that hyperbolic space is very different to Euclidean space. But there's also a more deeper, important meaning to this. And this deeper meaning is that rotation in a space is related inevitably to a circle, or that space's version of a circle, because the rotation of a vector won't change its length, it will just change its angle. So if we have a vector and rotate it, it will end up covering all points on the circumference of a circle whose radius is equal to the length of the vector. So if we're talking about rotating vectors, in other words, if we're talking about the overall vector being the same, but the components of the vector changing, then we are always defining it relative to, some kind of hypothetical circle in that space. But what's the circle in this space-time we're interested in our flat space-time with special relativity? Well, a circle is one of these hyperbola. So when we're talking about rotations, we're going to be defining rotations relative to a vector kind of moving along the boundary of one of these hyperbola. And And you might see that this hyperbola, if you know, we allow our space-time to become infinite in volume, then this hyperbola would be permitted, if we consider all events in space-time, to stretch to infinity, meaning that we could actually define, you know, angles all the way up to infinity, with each angle being distinct. Now that's a very unlike angles in Euclidean space, because for a circle in Euclidean space, as it's a closed curve, you'll eventually get back to the same angle you began at if you just keep rotating the vector. But that isn't the case with our vectors in hyperbolic space. And it will be kind of like having to take account of that when we're talking about the components of a vector changing but its size remaining the same in special relativity. In other words, when we're talking about kind of like how the space and time interval are different for different observers in special relativity. Because as we've said, yeah, we can define a vector where the length of the vector is preserved for different observers, but different observers will disagree on the components of the vector, so the space interval and the time interval. And so to describe that, we will naturally be making reference to kind of hyperbolic circles and rotation in hyperbolic space, but where we can define, you know, where we can define angles to infinity without having any kind of periodic repeating nature. And so, you know, all these things are going to become important, and it's because these hyperbola are the bedrock for really describing rotations, and therefore how to go from one observer to another in special relativity, that this space is very rightfully described as a hyperbolic space, because hyperbola play a fundamental role. So we've talked now about how strange hyperbolic space is. Now, don't worry if our discussion makes your head hurt. It is a very strange kind of space. Circles look very different, and therefore also notions of angles are extremely strange. But now we're going to go back to the idea of talking about the length of a vector. So before we were talking about the length of a vector which links events in space-time, and now we're going to describe that in a little more mathematical detail, and then we're going to generalize it to talk about vectors that live in space-time and transform in a way that their length is maintained even when we jump reference frames. And these kind of vectors we call four vectors. You know, this video is about finding the length of four vectors. In the next video we'll look at how the components change, and that will lead us to a discussion of Lorentz transformations. So, as we said before, we can consider a vector linking events in space-time, and there's nothing strange about doing that. And naturally, this vector is going to live in four-dimensional space, because we have one dimension of time and 3 dimensions of physical space. So, you know, by convention, we usually pick as first component to be a time-like component. Now, because physicists are very strange, they like having the first component being the 0th component. So when we're doing relativity, we start counting components from the number 0. I don't know why we do this. I don't know. I know in America it's fairly common to count from the number 0 in some cases. I don't know though why we do it. But anyway, if we have a 4 vector, and well, at least a vector with 4 components living in space-time, then its 0th component will refer to something regarding, something, well, a version of a quantity in terms of time, and then we'll also have a version of a quantity in our second component in terms of space. So for a vector linking events in space-time, the first quantity tells us how far apart events are in time, and our second quantity tells us how far apart events are in space. Now, I've dropped for this vector with 4 components the kind of d in front of our time and space intervals, because, you know, we can just go, well, we're going to define a point, and we're going to say at this point dx is 0 and dt is 0, and this point is the origin of our coordinate system. And in that case, if we label our axes ct for our time axis and x for our x-axis, then, or in other words, a space axis, then dt is going to be the same thing as just t, our value along the time axis, and similarly dx is going to be the same thing as x, our value along our spatial axis. So yeah, we can always do this. And so from now on, when I talk about, you know, vectors linking things in space-time, I'm always going to, you know, ignore our like dt and just write t, and ignore dx and just write x. So we can consider one of these vectors with 4 components being ctx. Now, x is the kind of like x itself with an arrow over it here is a vector which lives in 3-dimensional physical space, because it's kind of the vector describing distances in physical space, and so I use an arrow over the x to indicate that, you know, this kind of component x is itself kind of a vector. And I therefore have to use a different symbol to talk about the vector with 4 components, for which I use something called, I think it's called a tiddle. I can't quite remember the full name, I might be wrong with that, but it's kind of like a curly wave. So it's fairly common, although, you know, I don't think there's any superstandard convention, but it's fairly common to have a curly wave over a vector, at least in terms of special relativity, if it's a vector with 4 components, but an arrow over a vector if it's a vector concerning, you know, 3-dimensional physical space. And then for this vector we can define its length. So in other words, the length of a vector that links an event that occurs at the origin of our coordinate system to the event which occurs at time t and point vector x in physical space. We can describe the space-time interval associated with the length of this vector using this equation, where instead of writing x squared, I've wrote the scalar product of x with x, because based on how we define the scalar product, the length squared of a vector is just a vector scalar producted, if you like, with itself. And we're saying this dot here represents the scalar product, but the scalar product in the space of our 3-dimensional vector, and therefore it's a scalar product in, you know, Euclidean space, because remember, you know, 3-dimensional physical space is still Euclidean, so the scalar product there won't include any minus signs. So this is the same formula we had before, just now written explicitly in terms of a scalar product in 3-dimensional Euclidean space. And we can then rewrite the space-time interval in many ways. So the first way we can do is we can use matrix algebra to multiply our row vector by our column vector, and we'll end up with the expression we have in our middle blue box. That works. We can also consider it as a scalar product, but now a scalar product between vectors with 4 components, or like, vectors living in space-time, and therefore the scalar product will involve a minus sign, worth remembering. So if it's a scalar product between 3-dimensional vectors and figures that call space, no minus sign. If it's a scalar product between the vectors in 4-dimensional spacetime, there is a minus sign. The advantage, though, with using the matrix multiplication way of looking at it is it tells us that there's something subtle going on when we take the scalar product of a vector with itself in space-time. One of our vectors has a minus sign for the space term, and the other vector doesn't have a minus sign. And that's because really when you take the scalar products, you're kind of multiplying terms in your you're multiplying terms you've had between the contravariant and covariant version of a particular vector. So essentially your contravariant vector doesn't have any minus signs. Your covariant vector does. Now they're like two different types of the same vector. The contravariant vector is your actual, in this case, vector called 4-position. It's your actual vector living in 4-dimensional space-time, but to get the scalar product we need a covariant version if we could use the matrix algebra method, and the covariant therefore does include a minus sign to allow for the hyperbolic geometry of space-time. But you can write the space-time interval also slightly more simply in terms of tensor notation, as we have it as dx squared is equal to eta with 2 indices, so mu nu multiplied by x mu x nu. And essentially you sum over all values of mu and nu to get ds squared. Now, if you're not familiar with tensor algebra, it's worth saying more explicitly, for example, you just sum over all possible values of mu and nu, which range over your kind of like axes in space-time. So, for example, here ds squared would be eta 0 x 0 plus eta 1 x1 x1 plus eta 0 x0 x1 plus eta 10 x1 x0. But because eta 01 and eta 10, so if you like the non-diagonal components of our matrix, are 0, it means that at least for flat space-time we don't get any cross terms, and so we would end up with ds squared is equal to x0 x0 minus x1 x1. Now this eta mu nu is the kind of matrix present which tells us about whether the covariant and contravariant vector are going to be different, and how they're going to be different, and therefore define scalar products or distances in space-time. So the distances in space-time are really contained within this matrix, and this 2x2 matrix is our are kind of like matrix defining distances in space-time through the scalar product, and so we call it a metric. It tells us about how to calculate distances in this space. Now it's worth saying I said it was a 2x2 matrix, but if we're considering full 3 dimensions of physical space, then this -1 here would be replaced with minus an identity matrix, and et would actually be a 4x4 matrix. But because often for special relativity, something is just moving along one axis and we don't have to worry about something having motion in multiple axes, we can just pretend for practical purposes that there's only one axis of space and therefore write our Minkowski metric as a 2 by 2 metric. So this was fairly full of, bits of matrix algebra and tensor algebra. If you're unfamiliar with matrix algebra, I've got a video on matrix multiplication that's worth watching. If you're unclear about tensor algebra, I've also got a video about that where I do talk a little bit about the scalar product more generally than I have here. So there are videos to help with that. The important thing really is that there's a scalar product which gives us the length of a 4 vector, and all observers in special relativity agree on this length of the 4 vector, even though they might disagree on the components of this 4 vector. And now we'll be generalizing how this works in terms of 4 vectors generally, not just for position. On the next slide to conclude this discussion about how we find the lengths of 4 vectors and thus kind of quantities we can consider as invariant or quantities all observers will agree on the value of within the context of special relativity. So we have now come to the end of this video, or at least the last bit. Don't worry, we'll not just be ending immediately with a title screen saying generalising this, and then asking you to generalise from a blank, mostly blank bit of a video. We will be going through it, but we have now come near to the end of the video. I apologise for it being fairly long. I keep trying to make them, fairly short. However, at least having hopefully a bit of, realistic human interaction from, not fast, sped up, automated voice, hopefully makes it feel a little more comforting. And it's worth saying my words are not always, perfectly concise, but they are natural, and I hope that makes this physics at least a tad more approachable than reading it in some formal textbook. But the idea of space-time we have been building up is very important, and as well as the fairly unintuitive nature of space-time intervals as we have been describing them in terms of their hyperbolic nature and how we get them from the components of 4 vectors, there's something fairly more immediately obvious as being elegant about the nature of space-time. So if you place time on, let's say, your y-axis and space on your x-axis, then clearly light, if we take x to be, the distance light has kind of like has travelled, then c times t is going to have to equal x for light. Therefore, the motion of a light ray is going to be described by these lines. Light, or in other words, possibly information could have reached you from the past, affecting your present, or kind of you in the present could send out light beams and they could influence things in the future. Well, I mean, they equally, given where you are, you will only be able to travel into reaching events in space-time contained within these light cones, because you can't travel faster than the speed of light. Because to reach a region outside your light cones, your your distance you travel, so that say your value of x would have to exceed the distance light travelled, so ct, requiring you to travel faster than light. So because you can't travel faster than light, you are kind of like always going to, in your future self, all possible events will occur within your future light lane. And that's a fairly beautiful geometry, really. Um, Now, generalising back to four vectors, what we said about finding a invariant quantity from them, the general recipe is within special relativity. You firstly pick a reference frame because you have to we have to describe where events are in space-time using some axes in space-time. So you pick a particular reference frame, or in other words, a particular coordinate system. Now, usually, you will define the present and where you currently are um, um, to be the origin of your coordinate system, and you will consider motion relative to you and therefore relative to that coordinate system. So you would also usually have that origin move along with you to describe how events appear relative to you. But you don't have to do that. The important thing is you have a coordinate grid describing space-time. That is, you have some kind of reference frame to compare kind of events in space-time. And then you kind of consider a vector. Now with full position it links events in space-time. With other vectors it might link quantities associated with those events rather than the events themselves. But you have some kind of vector with four components. And the first component we usually call a time-like component, even though that's really only particularly meaningful, I would say, if we're considering our four vector to be full position. But our first component is generally called your time-like component, and then your if we're putting the space-like components into one, your second component will be your space-like component. But it's worth saying the second component is usually a vector itself, a three-dimensional vector that obeys Euclidean geometry. And then all observers, if this is a proper four-vector, so if this is kind of a vector whose length all observers will agree on, no matter the reference frame in which they describe this vector, so if our vector with four components is a proper four vector, then all observers will agree on a scalar quantity we can get by taking the dot product of the four vector with itself in hyperbolic geometry, which is the same thing as taking your time-like component, squaring it, and then minusing the square of your space-like component. Now, as we said, for full position, for our vector, which is full position, the scalar quantity is the space-time interval. However, for momentum, so we're considering not linking events in space-time themselves, but linking, say, momenta associated with events that occur in space-time. Then the associated scalar quantity with this vector of four momentum is the rest mass of an object. And so special relativity ends up guaranteeing that the rest mass, that is kind of how much mass an object has when it's not moving, is the same. Now you might say, well, it's strange to call it rest mass when we're saying that this is a quantity that doesn't depend on one's reference frame. the reason we do that is because, okay, yes, there is a quantity with mass that is independent of the reference frame, but in terms of if we're trying to move something and we're considering mass as resistance to kind of the object being accelerated, then that kind of mass can depend on the reference frame. So that is not an invariant quantity. Hence we use rest mass if we're talking specifically about the invariant mass of an object. And we use the term rest mass because this invariant mass is the same as kind of the more dynamic but non-invariant mass, but when viewed in the reference frame where that mass is stationary. So that's why we use the term rest mass, even though it's a quantity that actually all observers, whether they're at rest or not relative to the object, will agree on. But we'll come on to form momentum in a later video. This has been about understanding how we construct four vectors in space-time, how we link their components together to get a scalar product for the four vector, and how the way we link it implies that space-time does not have a Euclidean geometry but has a hyperbolic geometry. So this video has been about discussing quantities that are invariant in special relativity, and that's really important if we want to write equations of motions all observers will agree on. But there's another thing we might want to do in special relativity, which is to go, well, this is how I see events in space-time in my own reference frame, so how would somebody that is moving at a velocity v relative to me perceive those events? So in other words, how would the non-invariant components of a four-vector change when we jump reference frames? And as we said before, this is about rotations in hyperbolic space, so it will build on what we've said about hyperbolic space in this video. And so we're going to move on in the next couple of videos to talk about rotations in hyperbolic space and always keep it tied to relativity. And this will lead us to kind of explicitly working out a formula for, say, time dilation or length contraction, which we mentioned briefly in this video. And this will allow us to then start to talk about some of the practical effects of relativity. So, we'll be able to use ideas such as time dilation to derive the idea that there is energy associated with rest mass, so to derive E equals mc squared. We'll also be able to discuss experiments showing relativity, such as the very slow, seemingly decay of muons, at least in our own reference frame. We'll be able to link some ideas in relativity to certain ideas in general relativity. Linking special and general together. But we will also have videos once we've kind of done our work on kind of rotations in hyperbolic geometry on specific four vectors like form momentum. So we will cover, bits I have glossed over in this video in more detail. The important thing in this video is this general process for working out a scalar quantity in special relativity and the importance of finding these scalar quantities. And in the next video we'll be building to talk about time dilation, length contraction, and how kind of quantities we would usually consider in classical physics as being invariant do change, and come up with precise mathematical descriptions of how these things change.